覚悟して。この程度か。まだ立ってる。感謝するわ。満腹。どいて。虹の橋、その先を望むか。頑張れ、頑張れ。遅い。これでカリオストラにおまかお姉様、邪魔になるならばよし。アフェクションローク。アルスラグナー。天の山より下りし一撃を。カリオストラ、あとは私にやってくれるじゃないか。はっ、これでまだ大丈夫。とっておきの舞を見せてあげるわ。ペルペティオパスよ。我は万人の席を果たすのみよ。
Okay, good morning, everybody. This is a sound check. If you can hear me okay, can you please help to shout out in the chat box? Okay, thank you, everybody. Thanks for your feedback. Okay, I shall start shortly. Let's get my recording started. Okay. Meanwhile, I've restated the password on the chat box, so in case anybody requests, maybe somebody can help to post it again. Okay, good. All right. So good morning again. This is the tail end, the tail end of our topic on digital logic. Hopefully we can finish off the slide deck in 5-10 minutes. I don't know whether we can do this, but hopefully, yeah, we'll finish this last bit on programmable logic devices. But if you remember where we left off on Tuesday, we were talking about counters, yeah? The two type of counters. We have the ripple counter, which moves slower, okay, because when one flip-flop gets excited with the signal, the flip-flop at the end doesn't do anything, yeah? It just waits. No signal, nothing. But with the asynchronous counter, the signals are sent to all the flip-flops. So they potentially may be excited to change, okay? But whether or not it changes, it depends on the function, okay, the function that has been given to it. So these are the two different counters, and today we will tie up with programmable logic devices, and then we will talk about programmable logic array, or in short is PLA, and also Field Programmable Gate Array, which is the FPGA. Now all the abbreviations and all the different kinds of programmable logic devices, it's rather confusing. Okay, but it's okay. Just see what's available. What are the difference between them, and that's it. Okay, it's not a very big section anyway. So what is this thing called programmable logic devices? So the key word here is programmable. Okay, programmable. But if you notice so far, what we've been learning about, we have all the gates and all that, right? You have the AND gates, OR gates, NOT gates, and whatever. So all these gates are actually the building blocks for the functions. If you have a function, a Boolean function, it can be implemented using those gates. And of course, those gates are the basic building blocks. So what we have on the screen here are various devices to actually implement all those gates. And when devices are implemented, they don't just give you one device, like just one AND gate, one OR gate, or one NOT gate, or one NOR gate, or whatever. Manufacturers produce a number of chips on each of these devices. Okay, and some of these are actually pretty standard. You know, if you go on Google and you Google up 7400, okay, if you see the little number at the top there, 7400, or you Google 7404, and if you also include, let's say, circuit or something, it will return to you this so-called component which has n number of what gate and n number of, the specifications have already been fixed. Okay, so these are some of the integrated circuits out there that are being produced. Okay. Now, by the way, on the slide also, if you see SSI, all these are called the small scale integration kind of circuits. Okay. They are 1 to 10 gates on a single chip, right? Okay. By increasing the number of integration, or rather increasing the level of integration, you can put actually more gates on the chip. So of course, it will decrease the cost, decrease the size, and hopefully increase the speed. But of course, all these problems are that the interconnections need to be designed. Okay, that means how all these gates are being arranged to form the function takes time. And of course, to make custom chips, okay, that means you have a special chips to have certain gates that are interconnected. It's also costly and it takes time as well. Okay, this refers to custom chips, custom chip, not all these ready fabricated chips like this. So if you want something specific, to implement a specific function, then all these require cost and time. Okay, those are the custom chips. So how do we how are we able to develop a general purpose chip that can be adapted? Okay, that means we mass produce one general chip only, but yet that general chip can be adapted, meaning that it can be programmed. Okay, so that's where we come into programmable logic devices. Yeah, a logic device can be programmable. Okay, so that's where the general term of the PLD comes in. Programmable logic device, a general chip that can be adapted or programmed. Okay. Now, there are a few types of programmable logic devices. Okay, the first one I'm going to introduce here is what we call the programmable logic array, the PLA. Yeah. It's a small and simple PLD, programmable logic device, and it contains two levels. One is the AND part, and one is the OR part. Okay, and both are programmable. That means the combination of ANDs can be programmed, and after that, the combination of ORs can be programmed. Okay, so just remember, for PLA, you have two levels. One are the AND gates, and one are the OR gates. And then we can program them both. If you remember the sums of products, okay, when we want to have sums of products, we have a series of we have a series of AND gates so that we can do all the products. All the products will go to the AND gate, and after that, the AND gate will be OR so that we can get all the sums. Yeah, I hope you remember that one. Yeah, but the idea here is the same. Okay, the AND part and the OR part which you can program. Okay, now the other one, the name also is very similar. This is the programmable array logic. Okay, again, it's a very small PLD, and only the AND part is programmable. Okay, the AND part is programmable, but the OR part is fixed. Okay, the OR part is fixed. Why? I don't know. Because that's how all these designers have decided. Yes, okay, for this PL, for PAL, we will allow programmable AND, but the OR is fixed. Okay, so that's how they have decided it. Yeah.
It is also 2-level, Doctor?
Yes, there's 2 levels, but only one is programmable. Yeah. Okay. So and then on a wider scale, we can categorize all these programmable logic devices into the simple ones and the more complex ones. Okay. So for the simple ones, we have seen the PLA and the PAL. Okay, so that's considered simple already. Then we also have complex PLDs. Alright, complex PLDs, whereby the arrangements of the chips are actually more complicated. They actually go into a macro level. That means we have imagine many PLAs or many PALs put together. Okay, that's the complex PLD. Okay, another thing that we want to introduce here is field programmable gate array. Okay, what happens in this FPGA is that it allows more complicated logic functions. Okay, more complicated logic functions, and again, it has a wide number of inputs for the AND gates. Okay. It offers very more narrow logic resources so that it's very focused in its processing. It offers a higher number of flip-flops to actually implement all the various functions and what have you. Right? And generally, for FPGA, another good characteristic is the logic block, because then it shows the combination of all the various components in a bigger die, bigger layout bigger layout basically. Okay, and basically later I will show you another a diagram of the FPGA. Later I will show you a diagram of the FPGA. Now let's go back to, so now I've already introduced the basic few types, the PLA, the PAL, and the FPGA. Okay, so these are the, if you have to forget everything else, try to remember these 3. Okay, now let's go back to the PLA a little bit. Now all the Boolean functions can be expressed using SOP, okay, the sums of products, and it consists of NOT, AND, and OR gates. Okay, and all the various details, I think you can refer to the screen. Okay, but ultimately, this is roughly what it's going to look like. Okay, you have the AND part. Okay, and if you notice, the AND part will then potentially receive all the connections to the inputs. Okay, they potentially have connections to all the inputs, and then after that it goes into the OR part, and again all this can be potentially implemented. Okay, as it is, the diagram does not show what function it implements yet. All right. Now, how the PLA is manufactured, how is it programmed, is by fusing the connections. Okay, that means something. That means when a customer wants a particular function to be implemented, then the manufacturer will get all these specifications and fuse the certain connections together to implement that particular function. Okay, so like for example, on this diagram, I hope you can see those little dots where the connections are then finalized or fused, or whatever. So if you notice this one, the A here is as a little dot there. So A is in effect. This one, the B is in effect. This one, the not C is in effect. And all this goes to the AND gate, yeah? So this is going to be A, B, not C. Okay, A, B, not C. A and B and not C. Okay, A and B and not C. And then this one says not A, then this one is not B. So this one is not A and not B. And if you notice, going inside this OR gate, this one has been fused and this one has been fused. So that means we will take the AB not C and we also will take the not A not B. So that's why here you will notice at the bottom, this function will be AB not C or not A not B. Okay, there's a little bit of a diagrammatic. I've taken the image in total, but I didn't correct the notation here. This dot here should be the OR sign. It should be the OR sign. Similarly for the other one, it should be not A not B or not A not C. Okay, and if you notice this one also, the not A and not B is used twice, isn't it? So if you notice, this output here has been fused twice. Okay, it has been fused here and it has been fused here. So that's how, you know, some level of reusability, some level of flexibility is given in the PLA. All right. So I hope you know, if you forget everything about PLA, you remember this diagram. So oh yeah, you have all these gates available. You have one AND plane and one OR plane. Then you fuse them together. Then you get the output. So in this case, in this particular PLA, you get two functions. Okay, you get two functions out of this simple diagram here, right? So the PLA is just a simple example of a PLD. Okay, but what if the variety of functions that you need grows, you know, a lot? Now it just shows you two functions only. What if you want something that implements lots and lots and lots of functions? Okay, like for example, certain microcontrollers, for example, will require, you know, a large deal of functions, not just doing two functions only, right? So what if you have a large number of functions to implement? So FPGA might be an example, right? So it's the FPGA is, I was mentioning to you, it's like having multiple simple devices on a single chip, yeah? And of course, it has an array of uncommitted circuits. That means, again, all these are not fused yet. It's up to you to go in and do the fuse. But the canvas for you is much larger compared to the PLA or PAL. Yeah. So again, this is a very rough diagram of how the FPGA might look like schematically. So you have all the various logic blocks where inside you have, you know, all the PLAs or PL or whatever you want to call it. Okay, and all these are then interconnected. So it's like a multi-scale arrangement of PLAs or PALs or simple programmable logic devices, if you want to call it. Okay. Yeah, so all those logic blocks are either it can be combinational circuits or sequential circuits. Yeah, so that means inside the of course it's not shown, and of course it's not necessary for us to know how it is inside in detail. Why? Because we are learning computer science, not computer engineering. So we don't have to worry so much of the hardware side of it, but just let us know conceptually what's happening. So inside those logic blocks, basically you're having potentially something like this, which, you know, you select what you want to fire, or you select which function you want to choose. So a lot of these are done by triggering or selecting which logic block to activate and which logic function you want to activate. Okay, so if you can imagine, again, you have addresses or certain lines to select or trigger, and then you also go into a multiplexer, and ultimately the function comes out, or which block to activate, and so on. Yeah. Okay, so that's a general idea. And if you're interested to see what an FPGA looks like, once upon a time there's this company called Altera. Okay, In fact, Altera is well known for programmable logic devices. Okay? All their software engineers and all their engineers, their job is to look at
感謝するわ
circuit design, okay, circuit design, and they have sophisticated software in order for the engineers to actually design the functions to be implemented and all that, all based on customer specification. Okay, the customer will say, "Oh, this is what I want," la 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 la, and then they will produce a chip like this that can be mass produced or mass customized for the use of whatever device or microcontrollers or whatever they want to do. Okay. Altera, I think, has since merged with Intel. Okay, but at one time, a lot of our computer science graduates, they target to be employed in Altera. Why? Because among all the computer science graduates, Altera they pay one of the highest at that point in time. Okay. So it was a very popular place to apply for jobs after after graduation. But now they have been taken over. I mean, they have merged with Intel. Yeah. Okay, so I'm done. I'm done with digital logic, ranging from our Boolean functions, our combinational circuits, our sequential circuits. And now we have concluded with the programmable logic devices. Okay, now just very quickly down the chat box, what's the difference between fused and soldered? Yeah, it's something like soldered lah. It's something like soldered. But fused, of course, I think has a more general means. It just means that it's connected lah. Okay, it's joined together. All right. Yeah. Another way to call it is soldered lah. Can CPUs be considered a complex PLD? I think not. Why? Because CPUs, the i5, the i7s that you buy, it's already fabricated. It cannot be programmed. Okay. Whereas a complex, you're calling it complex PLD. It cannot be considered a complex PLD either because complex PLDs are programmable. Okay, the P there means programmable. But when you buy a chip for your computer, it's already prefabricated. It cannot be programmed, so it's not considered a PLD at all. Okay.
Doctor, you said there is two ways to program. One is fusing. What is the other one?
No, I think I didn't say there are two ways of fusing. There's only one way. I mean,
two ways of programming, not fusing.
Two ways of programming.
Programming logic devices.
Which slide was it? Do you remember?
I will get it to you. Slide 38.
Alamak. 38. But 38 is not.
No, it's not 38 with a new. No, not there. I mean, it's if you can say Control F, do Control F.
Yes, Control F.
Yeah. And search fuse, FUSE. Enter. Yes, this slide. PLA is manufactured in two ways.
Okay, here it says every possible connection is made through a fuse. Okay, and then the other one is proper connections made during fabrication. Okay. So this one actually, the programming can be done either, like for example, you get a specification, and then you go and make the connection happen. Okay, that means I don't know what machine they use, but there's a way to go and make that connection happen. Okay, but sometimes it is the other way that these PLAs are used is during mass fabrication. Okay, that means you don't just do one by one, but you have many of them made on the spot. Okay, so that's the other way, which also requires some degree of fusing, if you ask me. Okay, so it's just whether you make it whether you make it like customized individually, or you make it during fabrication, as in many at a time. Okay, but even if you do it many at a time, the thing is still done through fusing as well. Okay, I hope that roughly answers your question.
Okay.
Righto. FPGA or CPL. Okay. FPGA is a kind of complex PLD. Right. So there are two main categories of PLDs. One is a simple one and one is a complex one. So the simple one consists of PALs and PLAs. The complex ones are FPGA, one of them. Okay. So I hope that clarifies JE's question. Okay. Any other clarifications needed for programmable logic devices? All right, good. If there are no questions here, then I will then go into the next topic already. Yeah. Okay, this is the second last topic for my half of the course, and this is about addressing instruction sets and also instruction set characteristics and functions. Okay, so forget about all the Boolean stuff and all the digital logic stuff. We're now moving into another topic altogether on addressing an instruction set. Okay, so in this particular slide deck, we're going to talk about quite a few things. So I don't know whether we can finish today, but anyway, talking about memory locations and addresses and memory operations, what can be done to the memory, and also instructions and sequencing. Yeah, how do we show the notation? What kind of instructions are there? What kind of operands and what kind of operations? Okay, so, okay, let's go. Yeah, okay. Let's talk about memory locations. Memory locations. Whenever something needs to be implemented, something needs to be executed, all these operands and instructions are actually stored in memory. Okay, that means whatever you want to execute, all of them are actually stored in memory first. Okay, that's the basic stuff. And all this memory stuff, all this memory stuff, consists of millions and millions of storage cells. Okay, each of these are called a bit. Yeah, so imagine this is your hard disk, and of course the hard disk stores all your data and all that. So all of your data, all of your blah 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 are stored as bits. Okay, so each one or each zero is called a bit, and then a group of all these n bits is called a word. Okay, call a word. Not a byte yet. We're not talking about bytes. We're talking about a word. So imagine if your memory has yesterday Tuesday's example or in the tutorial if you recall, we talked about the ROM. Yeah, and in one of the questions we have 128 times 8. Correct? 128 times 8. So the 128 here means 128 locations, okay? And then in each location, there are 8 bits, okay? 8 bits. So in this example, that 8 bits refer to one word, okay? One word, all right? And not necessarily 8 bits is, not necessarily one word is 8 bits. This one word could be 16 bits, it could be 32 bits, it could be 64 bits, and different specifications.
Yeah,
right?
like a bit string or whatever its length, a bit string.
Bit string is again totally different. The string refers to your programming variable size. Okay, but here I'm talking about just the raw memory. The raw memory, it's when one location, how long is the word? Okay, so that's a collection of bits referring to the the width of the storage. Okay, the string is another issue altogether because the string refers to how many bits or how many characters or whatever you want to put together. But it could span more than one word. Okay, but here that one word. Oh yeah, and don't confuse with words in languages, English words or Chinese words or Arabic words, where it has contains more than one character. That is again a totally different thing. Don't confuse yourself. This is a memory word. A memory word contains a few bits. Stop at there. Okay, stop there. Huh? So yeah, I should have shown this diagram lah. Okay, so you have a memory location. Sorry, not you have a memory. You have a memory. Okay, and it consists of many words. Okay, you have the first word, second word, third word, and so on. And each word has that n bit length. Okay, that is the length of the word. Yeah, just leave it at that. Don't confuse yourself with strings lah, characters lah, blah blah blah. And all that, huh? Okay, so many computers have word lengths from 16 to 64 bits, as I was mentioning to you. Okay, and now we go to the byte. Okay, so 1 byte is 8 bits. Okay, so these are the basic stuff. So in the memory location, so let's say for example, yeah, if you have the memory, it has many locations. Yeah, each location is the word length. Okay, so each of these memory locations will contain potentially a few things. Okay, it can contain instructions. It can contain operands. It can be okay, and these operands can either be numbers, integers, floating point stuff, or characters. Okay, all of them stored in memory in that location itself. Okay, right. Interestingly, later also we will see how all these instructions. Sometimes it is instruction plus the operand. Sometimes it can be operand only, or different things can be stored in each memory location. Yeah. So this is an example. The one at the top is a signed integer. Okay, a signed integer and 32 bits. So you can imagine you have 1 bit for sign and 31 bits for the magnitude of the number. Okay. And then the bottom example is an example of storing characters. So that 32-bit word is then able to store 4 characters, 8-bit, 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 8-bit. Okay. If you recall, ASCII is only 7 bits, but here we put it into 8 bits so that it is chunkable. It's easy to identify. Instead of 7, a 7, a 7, then you have some balance there. Very leceh lah. So we have then 4 chunks of 8 bits to store each ASCII character. Okay. Just looking through the chat box. Word is more like a group of bits. Yeah. Okay. Good. Yeah. Thanks, Chihia. Okay. Good. Yeah. And then for instructions, let's look at instruction. Okay. So the earlier two is for like integers and characters. What about for instructions? Okay. Now for instructions, the memory word, okay, let's say 32 bits, that memory word has fields. Okay, fields. One field is the operation to tell the computer what to do. Is it an adding? Is it a moving? Is it a storing? Is it a multiplication or what? So that's the operation field. And then the rest is the operand. Okay, the operand. Now the operand could be an address, it could be a number, it could be whatever. Okay, that the operand that the operation needs to do on. Okay, so you have the operation on the operand. Yeah, and these two fields are potentially in an instruction in the memory word in the memory. Yeah, Hannah. Okay. So in order to access the location, okay, like for example this one, if you want to access the first word or if you want to access the second word, you need to have an address. Yeah. This is also useful for your tutorial for those who are in tutorial D. Yeah. To access the 128 locations, we need an address. Yeah. So that's a bit for you. So to access the memory, we need to have an address. And the address is expressed again in a binary convention. Okay. So it's 0 to 2 to the power of k minus 1. Okay. So if you have 128 locations, that means you need 7 bits. And then the address is expressed from 0 to 127. Yeah, like that. Okay, so that explains this one. Okay.
Doctor,
The
it
other
says
thing about
K minus 1. Sorry for interrupting.
yes, k minus
K,
one.
oh,
For example,
minus 1,
so
not for the exponent. It's for
not
the
for the
after
exponent, it's for the
exponent.
yes, yes, yes. Yeah, it's not a small, it's not a small font, it's a big font. Yeah.
Yes,
So
yes, yes.
uh
Sorry, doctor.
okay. Okay, the other thing I will talk about here is byte addressability. Oh, this is also complicated. Huh? Now, you not only address the word, but you can address the bytes of the word. Understand that? Okay. So, you see, it's not practical to address each bit, obviously. Yeah. For example, let's say if your word has 16 bit or your word has 32 bits, why do you want to access only that one bit? There's no point. Okay. It's like an apartment trying to address each person or trying to address each door. You know, your toilet door also has an address. Your kitchen door has an address. Your room door has an address. It's not practical. Yeah. So why not we only address each apartment? Okay. So if you have 8 apartments inside, each apartment has an address instead of addressing all the small stuff. Yeah. So usually it's practical to have a successive address for successive byte location. So let's say if you have 4 bytes, then each byte will have a successive address. So let's say 0, 1, 2, 3 like that. Then the next word will have 4, 5, 6, 7 like that. Yeah. So each byte will have a address. Okay. So yeah, I just gave you the example already. Yeah. So let's look at the diagram here. So since okay, this is an example of a 32-bit word. Okay, and each byte has an address. So we have address 0, address 1, address 2, address 3. Okay, for each byte. The next word will have 4, 5, 6, 7. But look at the address of the word. Okay, the address of the word is, for example, the first one is address 0. The next one is address 4. Yeah, which is perfectly fine because in many addressing that on the streets, you go around the streets, the housing area, very often the houses are not numbered consecutively. Okay, they are numbered like 2, 4, 6, 7, and then another set of houses that number them 1, 3, 5, 7. It's the same thing in the computer memory as well. Okay, the each word, they are skipped. Okay, 0, 4, 8, and so on. Why? Because uh the gap there is actually filled by the individual bytes address. Okay, so if you want to address the first word, then use address 0. The second word, then address 4. Why? Because the bytes, the individual bytes have their own address. Okay. Other
So I want to
instances,
address.
other
So I
sorry.
want to, sorry, doctor. So I want to address word 4, the byte address of 5. So the word 4 and the second byte. And the second byte.
Later you will
4
learn
and
that
5.
that is even not necessary because when we address memory, we just address the word address. We rarely want to actually go into the byte to address that byte. Okay, all right.
So the most important thing here is how the word itself is being addressed. 0,
Correct.
4, 8.
Yes. Yes. Correct. Okay.
Okay. Thanks.
Okay. There are some people on the some chat messages indicating that the lecture topic is not available. Oh yeah. It's actually available on. Okay, I will make it available on eLearn shortly. Okay, I forgot to put it on eLearn. Yeah, but I have it ready already for sure. Okay. Um, just like Mantisa, the exponent representation. Uh, just like Mantissa, the exponent representation. Are you referring to this one? This is just a normal 2 to the power of k, then minus 1. This is nothing to do with the floating point kind of thing. I'm not sure whether you got that confused. 2's complement, there's no 2's complement here. I'm not talking about 2's complement. So again, don't confuse yourself. Are there instances where address hold more than 8 bits? Or are all memories designed with the 8-bit storage in mind? No. It's not limited to 8 bits because different architectures will have different bit length and that kind of thing. So no, okay. The simple answer is no. You're not limited to an 8-bit address. Okay. If you're only limited to an 8-bit address, that means you only have 256 locations, which is very, very sad. Isn't it? If it's 8-bit address, you only have 256 locations. And I'm sure your hard disk has more than 256 locations, or your RAM has more than 256 locations. Yeah, so don't think that only the address only has 8 bits. Very popular. Sorry.
The K here indicates the number of bits
Yeah. The K refers to the number of bits. Okay.
of the word.
Of the no addressable locations. The word has nothing to do with the number of locations.
So I don't. What is K here? I don't know what's K here.
The K is the number of bits required to address the number of locations that you have. So if you have 128 locations, K will be 7. Okay, but in the word, you might have, let's say, I don't know, 8-bit word, 16-bit word, or any number of length. Okay, but your locations, I don't know, if you have 128 locations, then your K will be 7. If you have 256 locations, your K will be 8. If you have 512 locations, your K will be 9, and so on. Okay? So we are talking about how to address the locations, not the width of the word. Okay? The width of the word is different. The number of locations is different. Don't confuse the two.
Okay, but like, where does the K come from? Oh, I don't know. I don't know where the K come from. I know it's okay addresses.
The engineers will decide how many locations are there. So if I say that I have 128 locations, then the K is 7. If I have 1 kilo locations, then the K will be 10. I mean, it's the designer's decision. If you're talking about exam questions, then the exam questions will give you hints on how many locations there are. Just like the tutorial questions, there's 128 locations. So you need to know that it is 7 bits. Yeah?
Okay. So for complicating it, making it complicate on myself and the others. I'm sorry.
The other thing is maybe in a lot of my examples, I'm just using 8 bits or 7 bits. So you might confuse between the two. But yeah, the width length and the number of locations are two different issues. Okay?
Okay.
Each ASCII character is 7 bits. Yeah, if you recall the first topic, ASCII characters are only 7 bits. Okay, I mean, is there always 8 bits of data per address? No, again, addresses, it depends on the addressable locations. If you only have a certain number, if you only have 256 addressable locations, then your address will be 8 bits. Okay, but of course that's not true. You have definitely more than the 256 addressable locations.
Excuse me, doctor.
Yeah.
I'm the one who asked the question. Sorry.
Which one?
I think you misunderstood. What I meant was that let's talk about the address itself. Let's say we're talking about address 0 and 1, 2, 3, right? If I'm talking about just one single address, let's say address number 1, is there always 8 bits of data inside that one address?
Yes,
Just
because we're talking about byte addressability, you see. So
it's
byte addressability. So when you address 1 byte, there will be 8 bits because that's 8 bits is 1 byte. Yeah, 8 bits is 1 byte. So when it's byte addressability, so when you address that byte means it's 8 bits.
Okay, so every single address has 1 byte of information.
Every byte has
Okay, every address, let's say address
every
number one,
address.
address number two, all of them have 1 byte of information each.
Yes. So every location has 1 byte of information. Correct.
Okay, thank you.
Okay. The other complicated thing I think that might confuse some of you is that addressable locations. Okay, and then the bytes that are the address that are within the word. Okay, like for example now, I have actually two memory locations, but I have actually 8 addresses. Okay, I have 8 addresses. But okay, to clarify this a little bit, in let's say in exam questions or test questions, okay, we rarely have to talk about byte addressability. Very often we just give to you, okay, there are how many locations, that's all, and you don't have to bother about addressing all the individual bytes. Okay, that is as far as the ROM goes and whatever goes. Later, when you're introduced to the memory topic, that one you may be introduced to how you want to best deal with the number of locations and the number of bits required. Okay, but at this point in time, just remember that addressable locations and the bit length, the word length. Okay, so if it's kilobyte, addressability will each address have only 8,000 bits. So if it's kilobytes, so it's 1,000 bytes. Each address have 8,000 bits. No. Why do you want to do kilobyte addressability? Sorry, Mama, I don't quite understand your question because the concept here is byte addressability, meaning that each byte has its address. And of course, the word length is limited. So in this case, if it's 32 bits long, you have 4 bytes in the address. Okay. I don't see why you are talking about kilobyte addressability. I mean, kilobyte is just there's no such thing as kilobyte addressability. It's just like if you have 8,000 bits, then it'll be all arranged into more memory locations. So you have how many? 1,000 bytes. Okay, so that means you have more memory locations. That's all. Okay, but I have not heard of this thing called kilobyte addressability. Okay, hopefully you don't get too confused by all these terms. Okay, let's get confused some more. Okay, now look at this. We talk about byte addressability, right? And you see how the memory location address is being given. Okay, notice that on this example is given address 0 and address 4. Okay, address 0 and address 4, and you notice the byte numbering, the byte addressing. It has 0, 1, 2, 3, and then 4, 5, 6, 7. Okay? Now, this is what we call big endian way of labeling the bytes. Okay, or rather addressing the bytes. Okay, so that's the big endian one, whereby the lower byte addresses are used for the more significant bytes. That means the bytes on the left. See, the lower address, which is 0, is for the more significant bytes, which means the bytes on the left. Okay, and the higher address is for the less significant bytes, which is on the right. Okay, so it goes from 0, 1, 2, 3. To make it easier to remember, you see, big endian means you end with the bigger number. Okay, you end with the bigger address. So it goes from 0, 1, 2, 3. Okay. Now, the other way is actually the little endian addressing, whereby the lower byte address is for the less significant bit. Okay, that means the smaller address is for the writer byte. Okay. Now you ask me which one is being used, doctor. So I cannot tell you. Why? Because different designers, they choose different conventions. Some use big endian, some use little endian. Okay, so this is again an example when it's big endian, the one on the left is big endian. Notice the addresses are 0, 1, 2, 3. Then 4, 5, 6, 7. Little endian is the opposite. Okay, the address goes from starts from the right now. 0, 1, 2, 3, 4, 5, 6. But the address of the word remains the same. Okay, address of the word remains the same. So this is address 0. This one also address 0. This one address 4. This is address 4. Okay. Another analogy, the big endian is like reading in English. Okay. Little endian is like reading in Old Chinese or Arabic script or Jawi script. So you start from the right to the left. Okay. So that's just an analogy to big endian and little endian. Okay. 1 byte, 1 address. Yep. If it's byte addressability, then it's 8 bits per byte. No, Shahid, this byte addressability is about assigning addresses to bytes. That's all. Don't go into the issue about 8 bits, 1 byte. Just remember, every byte has an address. That's all it means by byte addressability. That's all. Okay, let's look at an example of how this little endian, big endian thing is implemented in a memory. Okay, so let's say if you have this program and you have done the declaration for all the variables. Okay, so you have this variable a, which is an integer, then some empty space as an integer, then you have a double integer, you have a character, this is a character string, yeah? And then you have a character array, yeah? You have an array, then you have a short integer, then you have a normal integer again. Okay, so you have this few variables. So on the left is little endian, on the left is big endian, on the right is little endian. So remember, every variable will have a content. You see in the comment on the right side here, these are the potential values that you want to put into the variable. Now, whatever content of that variable must actually look the same, no matter whether it's big endian or little endian. Okay, so imagine if you use English language or you use Arabic language, the meaning must be the same. No, okay. If I say apple in English and apple in Arabic, no matter how you do the writing, an apple is still an apple. Okay, so just be careful. Big endian, little endian, the meaning of the content must remain the same. Okay, so let's go into this. So A is supposed to be 1, 1, 1, 2, 1, 3, 1, 4. Okay, so that's the integer here. So in big endian, you start filling from the left to the right. Yeah, so that's why if you see 1, 1, 1, 2, 1, 3, 1, 4, so that fills up 1 byte. Okay, but for little endian, since the addresses start on the right side, you fill from the right side. Okay, so it's 1, 1, 1, 2, 1, 3, 1, 4. But now you'll tell me, doctor, why doesn't the 0, 0 is 1, 1? After that, the 0, 1 is 1, 2. And then 0, 2 is 1, 3. And then here, 0, 3 is 1, 4. Now, as I told you, an apple is an apple. It must look the same no matter whether it's big endian or little endian. So, but you start filling from the writer byte, okay, the writer chunk of your memory. So that's why you start on this side and it's still 1, 1, 1, 2, 1, 3, 1, 4. Okay, it must look the same. All right. Then the next one is a padding. So it's an empty space. Okay, so empty space. So I just in big endian, I just fill up the next available, and the little endian also I just fill up the next available, which is next to the integer. Yeah. Then you have a double integer. Okay, consists of 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 10. Okay, so here it fills up the entire word. Okay, because it requires double length. Okay, and of course, since it's already filled up the entire word, both will look the same. Okay, big endian also look like this. Big endian also, little endian also look like this, right? Then character string 3, 1, 3, 2, 3, 3, 3, 4. Okay, 3, 1, 3, 2, 3, 3, 3, 4. Then on the little endian side also must look 3, 1, 3, 2, 3, 3, 3, 4. Yeah, apple is an apple. Yeah. Okay, the interesting thing comes when you do arrays. Okay, now this A, B, C, D, E, F, G is put into an array, which means this is not apple anymore. This is A, P, P, L, E. Okay, it's put into separate cells or separate elements of the array. Understand? So when you look at it from the big endian point of view, it has A separate, separate, then B, and C, D, then E, F, G. Okay? So that is the big endian. But for the little endian one, look, it fills from the right to the left separately because those are separate array elements. Okay? So if you notice, A, B, C, D is now reversed from the big endian. Yeah? And then another E, F, G. But if you think about it, it's actually not reverse. It's not reverse. Why? Because all of them are actually separate. So here you A, here is A. This one is B, here is B. So it's not reverse. It's just that it's just filling up from different directions. That's all. Okay. So be careful when you talk about arrays because arrays will then be treated separately and not as a integer or not as a string or whatever. It's all separate elements. Then we have a short integer, which is then half the length of the regular integer. So you see 5152, and here 5152, they will look the same. This one is, I give you half an apple. App, okay? So app must look the same on this side. App will look the same on the other side. Okay? Yep. And then, yeah, the integer f will look the same like 1, 2, 3, 4, 1, 1, 1, 2, 1, 3, 1, 4. Okay? Doctor, is there any pros and cons for each type of address mapping? Now, what do you think? Is there any pros and cons? Is there any pros and cons? I mean, in effect, all the content can be shown both sides without any difference. Correct? So, to me, there are no pros and cons. It's just a design. It's just a design consideration. Okay. So if we have a sign number. Will it right side big endian and like sign number will at right side of big endian and little endian 0 left side? No, a number is a number. A number is it must look the same on little endian, it must look the same on big endian. Okay? Just like apple. The A, maybe it's a capital A or a small a to indicate whether it's a special apple or a normal apple, whether it's a positive number or a negative number. So once it's given to you like that, it must look the same on either side. That doesn't mean that the sign bit on the little endian will be reversed. No, it must look the same. Okay, it must look the same. Big endian more readable to humans. Yes, more readable to humans, but the computer doesn't care. Okay, because if the computer has already been programmed to read it like that, the computer doesn't care. Okay. Arabic people are humans. Yes, but because you have been trained to read it from right to left. So it's like the computer. If it has been programmed to read from right to left, then that's natural to the computer. For people who read Arabic script or Jawi script or the old Chinese script, they are used to reading it from right to left. That it's already in them. Yeah. So to the computer or to people who read right to left, there's no difference. Yeah, there's no difference. Okay. Well, we are pretty slow. Let me see. Word alignment. Okay. Okay. Let's finish this word alignment thing. Do a little bit of chat and then we can do a short break. Okay, word alignment basically means that all the addresses of those words are according to the number of bytes in the word. Okay, that's as simple as I can explain it already. So if your word length is, for example, 16 bits, okay, 16 bits, which means 16 bits, which means 2 bytes. Okay, 2 bytes. So your consecutive word addresses will be 0 to 4. That's it. If your word length is 32 bits, which means you have 4 bytes, so your word addresses will be 0, 4, 8, 12, 16, and so on. So it skips you skip the number of bytes in the word. Okay, so that's basically byte addressability. So let's do a quick chat here. If the word length is 64 bits, Okay. Then what will be the alignment for your word addresses? Can you all just shout out in your chat box? Yes. Okay. 0 because 64 bits means 8 bytes. So your thing will be 0, 8, 0, 8, 16, 24, and so on. Okay. I saw somewhere 0, 29, 26. Okay. That is not accurate, Bernard. Why? Because if it's 0, 0, 1, 2, 3, 4, 5, 6, 7. Sorry, 0, 1, 2, 3, 4, 5, 6, 7. Up to 7 is already 8 bytes. So your next address will need to start from 8. Okay, not 9. If your next address start from 9, that means you have already 9 bytes in that word already. Okay, so your Bernard's answer will be correct if you start with 1, then 1, then 9, and so on. But you start with 0, then it'll be 0, 8, and so on. Okay, so just be careful about that one. I accidentally placed my finger wrongly on the keyboard. Okay. Okay, answer accepted. All right, let's take a short break. Okay, let me see. Now it's just after 9. Okay, 8-minute break. We resume at 9:10. Okay, we resume at 9:10. Thank you. May I know when is our test? After the break, we will discuss. Okay?
至らんとするか。面白い。
頑張ろう、一緒に。私が守る。さあ踊りましょう。私の舞を見せてあげる。あなたを魅了してあげるわ。Creeping Shadow Lovely Phantom。覚悟して。Assault Blow。どいどいそこ。沈め。
終焉を鳴らせ。ギャラルホルン。
私たちの全力。リゾブルブリンガー。
この程度か。
これで当然クローン。頼むよ。覚悟して。守れなかった。カリオストロ、任せて。いたずらしちゃうぞ。
虹の橋、その先を望むか。
ありがとう。
Creeping Shadow。
頑張れ頑張れ。感謝するわ。
虹の橋、その先を望むか。神々へと至らんとするか。面白い。
Okay, hi everybody, we are back. Sorry for the delay because I had some other thing going on in the background, so I needed to delay a little bit. Okay, now I think at this juncture, I was about to do the poll, but I'm not sure whether everybody is around yet. If you're not here, do you mind to shout out in the chat box? Just kidding. Okay. I'm just wondering whether yeah, but I'm just wondering. I was about to ask those who are not here to shout out in the chat box so that I will know whether you're not here or not. Okay. All right. Let's continue. Okay. I plan to do a poll, but then on second thought, I think I'll run the poll towards the end of the class. Okay, so that we are sure people are around after the short break. So just hang on. I will run the poll, and we will then see what the conclusion is regarding our test. Okay, let's continue. Unfortunately, we are extremely slow in this slide deck. I don't know why. I think 100 over slides for this slide deck. I think we only covered more than just 20 over slides. Okay, very quickly. Okay, let's go memory operations now. What can be done on the memory? Okay. Now, of course, we want to access memory for various reasons. Okay, and one of the reasons why we want to access memory is because it contains numbers and characters and operands for us to actually do our processing. Okay, so the numbers and characters usually occupy one word. Okay, one word. One entire memory word will potentially store one number or one character and so on. Or sometimes a number of numbers, a few numbers or a few characters, depending on the number of bits that was allocated for that number or character. Okay. Yeah, so it could be numbers plural or characters plural. Okay. So for character strings, now we talk about strings. Now we talk about strings. So for character strings, usually what will be indicated is the starting character. Okay, so that means the beginning of the string will be indicated by an address, so that we will know that okay, this is the first character, and then successive byte locations will then be the next characters, okay, or whatever of the string, right? And it will also be indicated that what is the end of the string. It will be indicated, okay, this is now the end of the string, no more after that. Okay. So it's also expressed as an address. Okay? So in the memory location, you can store numbers, characters, or strings. Okay, character strings. What about operations? Those are what you can store, what you can store. But what can you do? What can you do? So to execute instructions, all those words potentially will contain instructions. Okay, instructions are not necessarily numbers or strings or whatever, but in order to do operations, the memory word will then contain an instruction. Okay, an instruction. And this instruction to be executed will then need to be transferred from the memory to the processor. Okay, memory to the processor, because the processor doesn't have the codes. Okay, the processor doesn't have the codes. The codes which contain the instructions need to come from memory. Okay, now the memory referred here is actually you can think of it as the RAM. Think of it as the RAM. Okay, so memory to processor. And then the operands and the results, okay, also needs to be transferred. But in this sense, the operands will then come from the memory to the processor, and after processing, it will go from the processor back to the memory. So it goes to and fro, okay, because when it goes to the processor, it is still an operand, and when it comes back to the memory, it is already the result. All right. So there are two very basic operations. Now there are hundreds of potential operations.
Doctor, the recording. Did you start? Sorry for interrupting.
Yeah, you didn't start the recording.
Thank you for reminding. Okay. Right. So there are basically two very basic operations. Okay. But of course there are many others, like addition, subtraction, multiplication, skip, shift, all these other operations. But the most basic, okay, that involves the memory is loading and storing. Okay, loading and storing. Loading is basically reading from the memory or fetching from memory and put it to the memory. Okay, put it to the processor. You load the thing. Or storing. Okay, that means after you have done some processing, you want to store it back to memory, and that's basically a writing process to the memory. Okay. So loading here refers to the processor sending an address. So the address is very important. Okay, when you talk about memory operations, address is very important. So the processor sends an address and requests a content to be read from memory. Okay, and that address refers to a memory address. And then the memory will then read the data and then send those whatever content of that location back to the processor. So that is what we call loading. Okay, we load a variable, for example, we load a variable from memory to the processor. Okay. Then what about storing? Storing, we want to store it to memory, right? And we will also need an address. Okay, we will also need an address. So the processor sends an address together with the data, and then it is then written to memory. Okay, and of course, when it's writing to memory, the original content of the memory will be erased. Okay, so this is a diagram, okay, or animation to show loading. So the processor sends an address to the memory, and then from the memory, it sends the data to the processor. That's loading. Okay, then storing, the processor sends an address with the data to the memory. Okay, and that's it. Now, what other operations are there besides loading and storing? Can you guys just quickly shout out in the chat box? What other potential operations can you do? Now, this can be memory related or not memory related. Delete, adding, okay. Subtraction, okay. Printing, okay. Yeah, all right. So, yeah, all those are examples of operations. Multiplication, yeah, okay. But some of your operations refer to the I/O kind of operations, or copy. I'm not sure about copy. But yeah, of course, copy is something like an instruction, right? But here we are trying to talk about the processors kind of operations. So to my knowledge, I don't think there's a copy operation as far as the the ALU and the whatever is concerned. The more common ones are the addition, subtraction, those logical operations like shifting, ending, ORing, all those kind of things. But printing, copying, not so common. We can check, but I don't know. But offhand, I don't recall printing, copying, and things like that. All right, let's go. Next section. We're talking about sequencing now. Okay, instructions and also the sequencing of instructions. But first, I think we need to know what are the basic instructions that the computer is capable of. Okay, so we basically do data transfer, like just now loading and storing and all that. So that's between the memory and the processor. So that's data transfer. We also have arithmetic and logic operations. So the addition, subtraction, multiplication. So some of those that you mentioned in the chat box just now are valid. Then you also have sequencing and control instructions like branching, skipping, calling. Okay, those are examples of sequencing and control. Yeah. And you also have I/O transfers, like testing a particular I/O. You test the printer, or you start an I/O, or you halt an I/O. Those are processor related regarding the I/O. Okay. But first, we need to know some notation because every time when we write an instruction, it is good to know some basic notation that we use to express the instruction. Okay. So the first group here involves the registers. Okay, the registers, and these are something like variables lah. Okay, imagine when you write your C programming, when you declare the variables, you're actually telling the processor that, hey, you want to reserve a memory in location for this variable, and indirectly it's actually some address lah that you're actually referring to. Okay, so variables are synonymous or analogous to addresses actually, right? So yeah, location, var1, A, B, C, X, Y, Z. Okay, so those are potential memory address. But sometimes when you want to have register address, we use R0, R1, R2, and all that kind of thing. Okay, so those are common notations for registers and memory. You also have popular I/O registers like data in, out status. All these are I/O registers. And how do we write them in an equation? Well, not an equation, a statement. Okay, a statement. So let's say, for example, the content from memory location LOC, lock. Okay, location. You want to store it into R1. So this is how you do lah. You draw an arrow. Okay. Or if you want to do an addition, the content of R1 plus content of R2 and put it into R3. So that's how you do the notation. Okay. We can also express all these statements as assembly language notation. Okay, so the earlier one is those register transfer notation. You use arrows and brackets and things like that. Or you can use assembly language notations. Like for example, the first one here, the content of a lock, you want to move it to R1. So in assembly language, this is roughly how you put it. Move lock to R1. Okay, so you put a lock, comma R1. That means from the lock, you move it to R1. Okay. Adding of two registers, like for example, the R1 plus R2 put to R3. You put add R1, R2, R3. Then the computer already knows that this R1 and R2 are your operands, and your R3 are your to store the result. Okay, so that is assembly language. Okay, so let me look through the chat box. IO stream. Shun Xian, what do you mean by that one? That's an include kind of declaration, not so much of the variables, right? This is load right. Oh, Shun Xian is a joke, alright. So I'm supposed to laugh. Okay. Very good lah. Y'all got sense of humor early in the morning. Okay, the arrow, it just means to put into lah. To put into. The arrow just means put into, something like that. Not necessarily load lah. Okay. Right, so those are the basic notations. Now let's look at the type of instructions. Very important. Now remember the type of instructions, but I think we need to rewind a little bit. Remember in the first topic itself, we were talking about the various functions of the computer. The computer does data processing, data storage, data movement, and control. Okay, so likewise, the kinds of instructions that we have will then conform to that as well. So then for the functional view, we notice how the control mechanism is in the middle. It accepts data, okay, and then it will either trigger some processing from the CPU, or it might trigger some data storage kind of thing. So all these control, memory, CPU, and I/O, they're all interlinked, okay, and these form the four basic functions, okay, four basic functions for the computer to implement. Okay, four basic functions. So likewise, for the instruction types, we'll then look at some of these basic functions as well. So different types of instructions require different programming language support. But I think we don't really have to bother about the high language programming support lah. Whatever you program, the computer will then know what to do lah. Okay, know what to do. Yeah, of course, it needs to be all these instructions support the high level programming language. When you type a print statement, or when you type when you type multiply, or you do addition, it will then trigger some of these lower level computer functions to be activated. Okay, so let's look at the first one, data processing. Okay, data processing. These are basically your arithmetic instructions, okay, to do the numerical data. Some of it may be logical instructions to operate on the bits. Okay, so arithmetic does the numerical data, addition, subtraction, The logic operations will manipulate the individual bits. Okay, like ANDing and ORing. You're actually looking at the individual bits to do the logic. But the arithmetic one, we are looking at it as a whole, or it's 8 plus 2 plus something. Okay, so you have to differentiate between numerical and bit at the bit level. Okay, so when you do processing, it can be at the numerical level, or it can be at the bit level. Yeah, so these are the data processing kind. The second group here is storage. Okay, storage, moving data around. Okay, it could be memory related, or it could be register related, but you need some of these instructions to do that. Okay, the data movement can also the third one is data movement. Okay, and this one, it involves I/O, right? Involves I/O. It might be from the mouse, it can be from the keyboard, it can be to the printer, to the monitor, and so on. So it transfers program and data into memory and results back. Okay, this is to the memory lah. But there might be also other I/O related movements to the keyboard and all that type of stuff. And the last one is the program flow. Okay, because normally what happens is that when you execute programs, the status of the processor will change. Okay, every instruction that you execute will produce a status. Like for example, if you do an addition, if the addition proceeds okay, then the status will be okay, right? If your let's say multiplication or your division is, let's say, divide by 0, and then the number becomes infinity, cannot compute kind of thing, then the status will indicate that it's a divide by 0 situation, something is wrong, hang or something. So the program flow will indicate the status, and the program flow will also indicate the flow of the program. Okay, because not all programs go instruction 1, instruction 2, instruction 3, instruction 4, instruction 5. Sometimes it will branch to somewhere else. So that is program control, diverting the sequence of the execution, right? So that is the instruction types. Aside from these instruction types, see, there are 4 instruction types, right? We have the processing, the memory, the I/O, and the control. Okay, now all these instructions can be expressed. Okay, can be expressed in different ways. Okay, in different ways, and one of these categorization is in the number of addresses that are contained in the instructions. Okay, I hope this is very clear. Yeah, we have all these, processing, storage, movement, program flow. Okay, all these are instruction types. So let's say, for example, arithmetic. Okay, arithmetic. You have addition, for example. You want to add numbers, correct? You want to add numbers. But how is this add numbers expressed in terms of an instruction format? Okay, what is inside that instruction? Do you have 3 addresses, 2 addresses, 1 address, or no address? Okay, so how is this add instruction expressed? So you have a variety of these formats. Okay, now let's go through one by one. Hopefully we can cover as many as we can. So let's look at a very simple example. Addition, just now I was mentioning to you. So you want to do A plus B store into C. Okay, A plus B store into C, right? Okay, now let's look at this 3 address instruction format. Okay, 3 address instruction. So if you look at this, A plus B store into C, or A plus B equals C, if you want to call it. It actually requires 3 address locations, yeah? Okay, 3 address locations. You have the operation, okay, you have the operation. Then the first address is the source 1. The second address is the source 2. And the third address is the destination. So if you want to think about it, your A is one address, which is source 1. B is the source 2, another address. And your C is the storing the result, right? Your destination. So that is the third address. Okay, third address. So you can express this A plus B equals C as an instruction with 3 addresses. Okay? All right. So let's look at an example, diagram. So 3 address instructions. So you have the operation, source 1, source 2, destination. So imagine if you have, let's say, 32 bits. Okay, 32 bits. A certain number of bits will be for your operation. A certain number of bits will be your source 1 address. A certain number of bits will be your source 2 address. And a certain number of bits will be for your destination address. Okay? Now, this is actually considered by most conventions too large to fit one word. Okay, too large to fit one word. Because you actually want more bits to store addresses. Alright? For your source 1, source 2, and destination, we want to have as many bits as possible to store the address. Because why? We want to address many locations, right? Yeah. So what we want is actually too big to actually store in one word. Okay. So perhaps 3 address instruction is not the best. I don't know. Okay, but it exists. Okay. Now, just a quick chat discussion here. With 3 address instruction, what are the consequences of having 3 addresses in one instruction? And of course, you have the operation. So what are the consequences? What are the pros and cons of having the 3 instructions packed into that one word? Overflow? But of course, this is not an arithmetic operation. So there is no technically an overflow in that sense. Okay? Requires less memory. Okay, Yasmin, you have that concept, okay? But you have to word it differently a little bit. In fact, I think I've already said the answer just now. Okay? So the consequence of having 3 address in one instruction is that you have limited space for expressing the addresses. Okay? You have limited space to express the addresses. So let's say you have 32 bits. Let's say you have 8-bit operation, 8-bit address 1, and 8-bit, source 1, source 2, and then 8-bit to store your destination. So imagine with 8 bits only, you can only address 256 locations from memory. How much variety can you store? Yeah, very limited. Yeah. So Yasmin's concept is correct. Okay. Fast access, not necessarily, because you are accessing memory words anyway. So no matter whether you have 3 addresses, 2 addresses, or 1 addresses, the memory will be just as fast. Or you mean that, or to get all the variables, is it? To get all the sources? Yeah, maybe it's faster. I've already gotten, in that address alone, in that instruction alone, I already know the addresses of all the 3 operands and I can do it faster. Yeah, maybe. More efficient, yes, maybe also. Okay, you have already all the 3 addresses, so maybe it's faster. Con is the bad. Yes, of course, con is the bad. More memory being used for such a small, simple instruction. More memory being used. Ikmal, I don't quite understand what you mean. More memory being used. But you see, that one instruction is still one word. So there's no additional memory involved. Okay. So I don't know, maybe you want to clarify, huh? Okay, but anyway, that's just one word, just one word alone. Right, thank you. Now let's go into 2 addresses now. See, you wanted originally A plus B equals a waste of space. Waste of space. I don't know. Yeah, it depends on your interpretation, but I don't know. Waste of space, maybe. Yeah. Okay, sorry, get back to this one. You wanted A plus B equals C. Okay? But if you think about it, after you have read A and the B, you don't need the A and B anymore, right? Why not reuse one of those variables? So you see, you can do A plus B and then store it into B, isn't it? So with that, you actually only need 2 addresses, right? One of the source address, you can recycle it as your destination address. Okay, so in the end, you actually only need 2 addresses, right? So the format, okay, look at the bottom there. You have operation, source, and your destination. Why? Because the destination is recycled. It has been used as the source before, and then sorry. Let me rephrase that. You have source and your destination, but to effect the A plus B equals to B, you then recycle the destination address. Okay, so if you look at this one, add A B, so you're actually adding A plus B, and then you store it into B. Okay, so that means the destination address works as the source, and then after that is used as the destination. Okay. Now, if you are very particular about having A plus B, then must store into C. Okay. Then one suggestion is that you need 2 instructions. Okay, 2 instructions. So for example, you move B into variable C. Okay, you still need 2 addresses here, 2 address instruction. You move B into C. So that means in the C, you have the content of B. All right, and then you add A to the C. Okay, I hope you understand this one.
Doctor, 2 address, 3 address are all just categorizing of instructions.
Yes, different way of formatting the instructions. Different way of implementing the same thing. Okay, you can
the memory.
Yeah, stored in the memory. Okay, so so assume that you have a storage C here. So you put the B, you store it into C first. Okay, and then after that the A, you add it into C. So in the end, C is actually A plus B. Okay, now this one, if you really want to have another variable C. Okay, but if you look at the instruction, each instruction has 2 addresses. Okay, that's what I'm trying to say. You can implement the same thing but using 2 instructions, but it will look longer. You need 2 instructions now. Okay, right. 1 address instruction. Now this is where it gets complicated. Now, when you have 1 address instruction, how do you get the other operand in order for you to do some kind of operation? Let's say, for example, if you want to do A plus B, you need to have variable A and you need to have variable B. So how am I going to do this with only 1 variable? I cannot just like add A. What about my B, right? So I need at least 2 locations. All right. Now the solution to this is that you have an implied variable. Okay, an implicit variable that is there all the time to store one of the variables. Okay, so for these purposes, we have what we call an accumulator. Okay, an accumulator. it is a special register. Okay, it's a special register and it is implied. Okay, you don't need an address for it. You don't need an address for the accumulator. So when you say add A, okay, you add A to what? You add A to the accumulator, okay? Because the address of the accumulator, the content of the accumulator is ready there. It's already waiting for another operation to be done on it. Okay, so that's why we don't need an address for it. Okay, so if B is 2, you move B to C, then C. Yeah lah. So you're just putting the variable inside lah. Okay, Ali. Yeah. All right. So for one address instruction, so basically it's going to look like this. You have an operation with a source/destination. Okay, so that one address can be used for the source. It can be used for the destination. Right. And how do we do A plus B equals C? Then you have this one. Look at that. There's 3 instructions now. There are 3 instructions. So we load A. Yeah, assuming here is the accumulator. Where is my pen? Okay. Okay, so this is the accumulator. It's a special register. So it says load A. Okay, load A. Now it just says load A only, but load A to where? Automatically is implied accumulator. Okay, so you load A. Then you add B. Add B to what? Add B to accumulator because it's implied. So you add B to whatever is already in the accumulator. Then you store C, assuming that in the memory you have a variable C there, some location in memory. So you say store C. Store what to C? Store accumulator to C. Okay, so this content here is then transferred to C. So in the end, C equals to A plus B. All right. So this is how, if you look at all these instructions here, all of them have only one address inside. Okay, they will all look like this. Okay. Right. Another quick chat shout out. If you have one address instruction, what are the consequences of having one address in one instruction? Okay, so what is the consequence here?
So while they type, could you please go back to the previous slide? Yes. You mean this format or this destination or this address is for load, then another one same to it for add B, then another one for it to store C, or all of these 3 are in this one address?
One address. Okay, these are 3 instructions. Okay, instruction 1, instruction 2, instruction 3. And all these 3 instructions contain only one address. Okay, so you can imagine. Okay, let me do this lah. Okay.
So we have 3 rectangles.
3 instructions.
Yeah.
3 instructions. So the first instruction here, second instruction, third instruction. So this operation will be a load operation. Load what? Load address A. Then this one is add what? Add address B. Then here is store. Store what? Store address C. Like this. So you have 3 separate instructions, but in each instruction, you can only express one address. Okay?
This is when using assembly language.
This one is expressed in assembly language. Okay?
What is the implementation of this, or how are we going? I know this question might be not good, but how are we going to use this?
How are we going to use this? That one is actually more on the computer engineering side, where it is then done into the circuit level. Okay, at the circuit level, then everything will be in bits and bytes. So imagine the store maybe it's expressed as 0010000. So the computer will then read, oh, this one is store. Then the address C could be, I don't know, 0001010000000, and then it's then put into a circuit with all the gates and all that, and then it does the computation. Okay, of course that is beyond our discussion. Yeah, it's a much more complicated thing out there. Okay. Okay, back to the chat here. Need more instruction? Yes. So if Hu Ying, if you notice, for 3 address instruction, we only needed 1 instruction to count in the thing, right? When you move to 1 address instruction, we needed 3 instructions in order to finish the to actually carry out A plus B equals C. Okay, more steps, yeah, more steps, more instructions can have greater value. Yes, you have a greater magnitude to express the address, not necessarily the value. Okay, not necessarily the value. We have more addressable address. Okay, the magnitude of the number that you want to add depends on the length of the word. Okay, not the addressable locations. Now notice that the discussion here, all this A plus B plus C and all that, the A refers to an address in memory. Okay, an address in memory, and that address A contains the number or whatever operand that you want to do. Okay, we're talking about addresses, not numbers. Okay. Yes, scout team. Yeah. Okay. Right. So your discussions there are valid. So with 1 address instruction, the consequence is that you need more addresses, and but the plus point here is that you have more addressable locations. Okay, more addressable locations. Does accumulator need to be reset? But in this case, not really, unless you really want to reset it. But in our discussion today, the resetting of the accumulator doesn't come into the picture. Okay.
The pros of it is more addressable addresses, right?
More addressable locations, not addressable addresses. More addressable locations in memory. Okay.
Okay.
Okay. What if there's something already in the accumulator? Yeah. That's why it depends on your programming. Like if you really need to like reset something to initialize something, then you probably need an instruction to initialize the content. Okay. Lesser memory. Oh, I think this was from the earlier discussion. Okay, never mind. All right. Okay. So done with 1 address instruction. Now, do I have time for this one? No lah. Okay, I think I will reserve this for next week. Okay, because 0 address instruction is a little bit complicated. Yeah. All right. So I think I'm done with the whatever I can for the slide deck today. So I think now we better discuss the test. Okay, test 1. Okay, I'm going to release another poll. Yeah, I realized that somebody was suggesting why not we do another poll, and then I was reluctant to do the next poll because I thought we already decided from the first poll. But then I think it now it has come to a situation whereby I think a second poll is necessary lah. So what I'm going to do is I'm going to release a poll. The options are four options. One is next Tuesday, which I think many people won't like. The other one is next Friday. Some of you like, some of you don't like. The third option is sometime during the break. Okay, again, some of you like, some of you don't like. And I have one more option. Okay, I have decided to have this option after I've consulted Dr. Manmeet. Now, the fourth option is to do it on the Tuesday after the break. Okay, which means 8th of December when you come back after the mid-sem break, the first class. Okay, instead of Dr. Manmeet taking over. That day we will do the test. Okay, but not necessarily at 2 o'clock. Okay, not necessarily at 2 o'clock because Tuesday's class is supposed to be at 2 o'clock. Well, if 2 o'clock is okay, we can run it at 2 o'clock. Otherwise, we can actually run it a little bit later. Okay, but I'm talking about the day. I'm talking about the day. So it's either next Tuesday, next Friday, sometime during the break, or after the break, the Tuesday. Okay. Please after the break. Wait. Okay, Hu Ying has introduced another Cantonese word, kanjiong. Kanjiong means exciting or exciting. I think is the word. Kanjiong. All right. Can I have this PowerPoint? Yes, yes. I will release the PowerPoint. I forgot to upload. Very, very sorry. Yeah. Doctor, for test one, will cover until which topic? The later the test is, I think we will cover more topics. Okay, just kidding. I think the most I will cover, I think, is this slide deck lah, until instructions and instruction formats. Okay. um. Okay, sounds good. Sounds good. I don't know which I don't know which one sounds good. Please after the break. After the break. No, 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 no. Please before break. After the break means it will cover all the topics. Yeah, Divaga was right. He already said it before I said it and laughed. After the break, please Friday. Okay, we will let you all decide. If there are no other options, then I will then release the poll already. Let me rest during the break. Yeah. No more delays, more chapter to study. Oh, never mind. Hey, why so many chat messages one? Okay. This is the problem. I think I'm being too nice. Oh, which option do you want? And then now we have this problem, right? Maybe I should be more autocratic. Okay, next Friday, and then you cow team already. Yeah. Too nice. Also problem. Okay. Let's not waste time. I'm going to start the poll now. This is like the Kahoot quiz or tom chak boom chak boom chak. Too bad there's no music. Too bad there's no music. Maybe I'll just do some beatbox with my mouth or something like that. But then I won't do it. I won't do it. Okay. Good grief. Can you guys see the results of the poll? No, okay. Only I can see. For me, it's very kanchong lah. I can see the numbers changing all the time. Oh dear. Oh yeah, maybe after the poll has ended, you can see the results. Maybe I don't know because I'm on the the facilitator end, so I don't know what you guys see. Um, yeah, this is very exciting. I can see the number changing. uh, oh, share the screen. Yeah, that's a good idea. No, 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 no. I won't share the screen because then they will influence the influence the choice of the other people who haven't responded. Okay. I think you guys are almost done. Out of 170 over of you, there's 30 something people haven't answered. So I don't know whether they are actually joining the I don't know whether they are just logged in without following the lecture or what. Now the numbers are increasing again. I don't know. Are you guys discussing with each other? Is it? Come, all of us put choice B, all of us put choice C or something. Then only the numbers you decide. Okay. That's an update lah. As I'm looking at the numbers, we actually have a majority here already. So funny lah, you all. Fake news. Trump wins. Biden wins. Now. Okay, there's less than 2 minutes. I do not know whether the rest of you will actually make a difference. Okay, those who haven't answered remain the same. Okay, I think I tell you what. Oh no, somebody just answered. Okay. See, now the numbers are reducing again. I don't know. You guys are taking a long time to answer. Goodness. Looks like a very difficult choice, very important, right? Yeah. Choosing between A, B, C, D will be like, oh, life and death. So now I better choose wisely. Oh dear, the number is still, some people are still voting. Okay, never mind, never mind. Everybody has the right to vote. Okay, less than 45 seconds now. Tough choice, huh? Yeah, it really is a tough choice. Hardest multiple choice question. Yeah, you're very kelakar lah, you. Okay, another 15 seconds. Still people answering. Goodness. Number is still changing. Oh, kelakar is very funny, humorous, joking. So to those who don't understand, kelakar lah you all. Oh, okay. Say the last 10 seconds. Okay, we are done. Can you see the results? Can you see the results? No, you can't see the results. Okay, I see whether I can show you the screen then. I'll stop sharing this and I'll share my screen. Just a minute. I think my mouse is having some problems. Share with attendees poll results. Okay, sorry, I missed that. I missed that one. Okay, so you guys saw the results, huh? All right, so it looks like yeah, almost a majority lah prefer on Friday lah. A very small number during the break and next the following week. Okay, so it'll be Friday lah. It'll be Friday, and yeah, I do understand some of you have another test on Friday night and all that. But I think we have to come to a decision somehow. I think was it Michelle? Michelle, you also have a test on Friday. Okay, but what time? I shall. Okay, because on Friday we have a tutorial from 3 to 4, so I will either schedule it after 4 lah, maybe between 4 and 6 o'clock like that, so that you know, it allows the people in the Middle East to have a comfortable, you know, morning, and also sufficient time for people who are having the test at night to also have a breather lah. Okay. Test format, you'll be like short answers. I haven't decided whether to have MCQ or not, but at least prepare for short answers. You'll be chapters 1 to chapter on the instructions and instruction formats. Okay, the topic that we're covering now, the topic that we're covering now. Okay. Sorry, just let me get my chat messages. Test format, how long? Okay. Since it's going to be online, I will make it like asynchronous style. Okay, it won't be like you know 1 hour you start and then end. Due to the due to the asynchronous nature, I'll give some leeway, but I will open it at one time and then I will close it at a certain time. But when you attempt, you are given a limited time. Okay, so that will give you some flexibility when to start and all that lah. Okay. Okay, from 4 to 6 is 8 in the morning, is it? Hope to have MCQ. All right. Okay. All right. Okay. So I think it's settled lah. It's next Friday. Roughly around 4 to 6 p.m. I will then give instructions either on eLearn or in the lectures next week lah. All right. What chapter again? I don't remember the chapter number. Let me see. This chapter is chapter 5. Okay, topic number 5, which is on addressing instruction sets, characteristics, and functions. Okay. That means I will upload the slides shortly after this, and that will be the topic that we covered lah, from the topic 1 until topic 5. All right. Okay. I hope I've covered everything. Right, if there's no further questions, so thank you very much for joining the lecture today. Have a good weekend and bye-bye.